Good evening, and welcome to the Late Lab. I'm very glad you've joined me. Before we settle into tonight's subject, tell me where you're listening from. Perhaps you're tucked beneath the covers, watching the lights pass by from a late train, or resting somewhere quiet with the day finally behind you. Wherever you happen to be, I hope you feel warm, unhurried, and ready to let your thoughts wander for a while. And if these slow journeys through science help you relax, leaving a like and subscribing is a simple way to support the channel and help it continue growing. To everyone who has already subscribed and returned for another evening, thank you. It genuinely means a great deal. Tonight, we are exploring one of the strangest questions in all of quantum physics. The wave function sits at the center of the theory, predicts experiments with astonishing accuracy, and yet physicists still cannot agree on what it actually is. It may describe something physically real. It may represent information. It may guide particles, contain entire branching realities, or reflect only the relationship between one system and another. I'll do my best not to make that mystery quite interesting enough to interfere with your sleep. Although, if you do remain awake, at least you can spend the night wondering whether reality itself exists in a vast invisible wave across an unimaginable number of dimensions. Very restful. So let us begin. What is the quantum wave function, and why, after a century of successful physics, do we still not know whether it is real? At the center of quantum mechanics sits an object that no one has ever seen directly, yet almost every prediction in the theory depends upon it. It is called the quantum wave function. In the mathematics, the wave function describes the state of a quantum system. It tells physicists how to calculate the probabilities of different outcomes, whether they're asking where an electron might be detected, what energy an atom may possess, or how likely a particle is to pass through a particular region. This mathematical object is extraordinarily successful. Quantum mechanics has been tested in laboratories for roughly a century, and its predictions agree with experiments to astonishing precision. The theory underlies lasers, transistors, magnetic resonance imaging, atomic clocks, and much of modern electronics. Yet the wave function itself remains strangely elusive. Physicists know how to use it. They do not agree on what it is. An electron provides a simple example. In ordinary classical physics, a particle is imagined as a tiny object with a definite position and a definite motion, whether or not anyone happens to know those details. Quantum mechanics does not usually describe an electron in that way. Before a measurement, the theory may assign a range of possible positions, momenta, or paths, each associated with a probability amplitude. The electron is not merely hiding one definite answer from us in the familiar classical sense. The structure of the theory allows different possibilities to interfere with one another, which is something ordinary ignorance cannot do. This is where the word wave begins to cause trouble. A water wave is a changing height in the surface of water. A sound wave is a changing pressure moving through air or another material. An electromagnetic wave is a changing pattern in electric and magnetic fields. In each case, we can say what is waving. The quantum wave function is not automatically that kind of object. For a single particle, it can sometimes be represented as a pattern spread across ordinary three-dimensional space, which makes the comparison tempting. But even there, its values are not directly measurable in the same way as water height or air pressure. For several particles, the wave function usually belongs to a much larger mathematical space containing every possible arrangement of the whole system. That makes it very difficult to picture as a simple physical ripple travelling through the room. The mathematics itself is not the main source of disagreement. Physicists largely agree on the formal rules used to calculate experimental predictions. They agree on how the wave function changes according to the Schrödinger equation, and how probabilities are extracted through the rule introduced by Max Born. Laboratories around the world use the same framework and obtain the same results. The disagreement begins when someone asks what the mathematics says exists. One possibility is that the wave function is physically real. It may be a genuine part of nature, even if it exists in a form unlike any classical object. Another view treats it as knowledge, information, or expectation about possible measurement outcomes. In that picture, a change in the wave function may resemble an update in what can reasonably be predicted rather than a physical wave collapsing across space. Other interpretations give it different roles. In pilot wave theory, the wave function guides particles that possess definite positions. In the many worlds interpretation, the universal wave function never collapses and instead contains branching histories associated with different outcomes. Relational quantum mechanics treats a quantum state as meaningful relative to interactions between physical systems. Objective collapse theories propose that the wave function is real and sometimes undergoes an actual spontaneous reduction. There is also the possibility that quantum mechanics is incomplete and that a deeper theory will eventually reveal what the wave function was describing all along. So when physicists say they do not know whether the quantum wave function is real, they are not confessing that quantum mechanics has failed. Quite the opposite. The predictions work almost embarrassingly well. The uncertainty concerns ontology, the study of what exists at the most fundamental level. The wave function may be a physical entity, a law-like structure, a description of information, a relation between systems, or a sign that our usual categories are too narrow. What makes the mystery so unusual is that the same object can be mathematically indispensable and physically obscure. We can calculate with it, test it, and build technologies from its predictions, while still asking the quietest and most basic question of all. What, if anything, is really waving? Long before physicists spoke of wave functions, probability amplitudes, or particles existing in superpositions, the physical world appeared to be made from things with definite properties. A stone occupied a particular place, a planet followed a particular path, a moving object possessed a measurable speed and direction, even when no one happened to be watching it. This classical picture reached its most influential form through the work of Isaac Newton. In Newtonian mechanics, the state of a particle could be described by its position and velocity at a given moment. Once those details were known, along with the forces acting upon it, its future motion could in principle be calculated. A thrown ball followed a continuous trajectory through the air. The moon moved around Earth under the influence of gravity. The planets travelled along paths determined by their initial motion and the gravitational pull of the sun. The equations did not merely predict where an object might be found, they described where it actually was at every moment along the way. There could still be uncertainty, of course. A person might fail to measure the position of a cannonball precisely or might not know the exact strength of the wind. But this uncertainty was understood as a limitation in human knowledge. The cannonball itself was not uncertain. It had one position and one velocity, whether anyone knew them or not. Waves belonged to a different but equally understandable category. A water wave was not a compact object following one narrow path. It was an extended disturbance spread across the surface of the water. A sound wave consisted of changing pressure and density moving through air, water, or another material. Different regions of the wave could be rising, falling, compressing, or expanding at the same time. The amplitude of a wave described the size of its disturbance. Its wavelength described the distance between repeating features, such as one crest and the next. Its phase described where it was within its repeating cycle. These quantities varied continuously across space and time, producing patterns that could be observed and measured. When two waves crossed, they could interfere. If their crests and troughs aligned, their amplitudes reinforced one another through constructive interference. If a crest met a trough, they could partially or completely cancel through destructive interference. Nothing mysterious had to decide which effect occurred. The result followed from the physical shapes and phases of the waves. Light eventually became part of this wave picture. During the 19th century, James Clerk Maxwell showed that electricity and magnetism were not separate collections of curious effects. They were connected aspects of a unified electromagnetic field. Maxwell's equations predicted that changing electric fields generate magnetic fields. while changing magnetic fields generate electric fields. These linked disturbances could travel through space as electromagnetic waves. The calculated speed of those waves matched the measured speed of light, revealing that visible light was one small region within a much broader electromagnetic spectrum. This was a remarkable unification. Light was no longer simply a ray moving from one place to another. It could be understood as a real, continuously changing pattern in electric and magnetic fields. Unlike sound, it did not require air or another material medium. The electromagnetic field itself carried the disturbance. Classical physics therefore offered two broad and apparently clear kinds of description. A particle state specified the properties of a localized object, including where it was and how it was moving. A wave state specified the condition of an extended medium or field across many locations. The distinction was not always perfectly tidy, but it was conceptually comfortable. Particles travelled, waves spread, particles followed trajectories, waves interfered. A planet did not cancel itself out by passing around both sides of the sun. An ocean wave did not arrive at the shore as one tiny, indivisible speck of water. This success encouraged a powerful expectation. A useful mathematical equation should correspond to some comprehensible physical mechanism. Newton's equations described bodies responding to forces. Maxwell's equations described changing electromagnetic fields. Even when the mathematics became difficult, physicists could usually tell a story about what the quantities represented in the world. The quantum wave function inherited much of the language of classical waves. It possessed amplitude, phase, wavelength, and the ability to interfere. Yet these familiar words no longer pointed towards one familiar physical picture. An electron could produce interference, as though something extended had travelled through several possible regions. When detected, however, it appeared as one complete localized event. It did not arrive as a faint smear spread evenly across the detector. The comfortable separation between particles and waves had begun to fail. The mathematics behaved like a wave, while the experiment recorded something particle-like. And so, a new question quietly entered physics. What exactly could be waving when the thing being described always appeared in one definite place? At the beginning of the 19th century, light seemed to have found a comfortable identity. It behaved like a wave. Thomas Young made that conclusion difficult to avoid with his double-slit experiment. A beam of light was directed towards a barrier containing two narrow openings, with a screen beyond them. If light behaved only like a stream of classical particles, each particle might pass through one slit or the other, producing two bright regions. That is not what appeared. Instead, the screen developed alternating bright and dark bands. Bright regions formed where contributions from the two slits arrived in phase, allowing their amplitudes to reinforce through constructive interference. Dark regions formed where they arrived out of phase, causing one contribution to cancel the other through destructive interference. This pattern was characteristic of waves. Water waves passing through two gaps produce similar regions of reinforcement and cancellation. So did sound waves. Thomas Young's results showed that light could spread through both openings and combine with itself in a way that ordinary particles could not. During the 19th century, the wave picture became stronger. James Clerk Maxwell's theory identified light as an electromagnetic wave, a changing pattern in electric and magnetic fields travelling through space. Light seemed to have chosen its side. Then the opening decades of the 20th century made that choice far less secure. In 1900, Max Planck studied the radiation emitted by heated objects. Classical physics could not reproduce the observed spectrum at all wavelengths. Planck solved the problem by proposing that energy was exchanged in discrete amounts, later called quanta. The implications were unsettling. Classical waves were expected to exchange energy continuously. Planck's result suggested that nature sometimes transferred energy in separate portions. Albert Einstein pushed the idea further in 1905 while explaining the photoelectric effect. When light shines on certain metals, electrons can be ejected from the surface. Classical wave theory suggested that brighter light should eventually provide enough energy, regardless of its frequency. Experiments showed otherwise. Below a threshold frequency, no electrons were released, however intense the light became. Above it, electrons could be emitted almost immediately. Increasing the frequency raised their energy, while increasing the intensity mainly increased how many were emitted. Einstein proposed that light transfers energy in discrete packets, later called photons. The energy of each photon depends on the light's frequency. One photon can interact with one electron in a localized event, rather than spreading its energy across the metal. Light now appeared to possess two incompatible personalities. It produced interference like an extended wave, yet transferred energy like a collection of particles. This same phenomenon resisted either classical category. Louis de Broglie then reversed the argument. If light, once understood as a wave, could behave like particles, perhaps matter, normally understood as particles, could behave like waves. In 1924, Louis de Broglie proposed that a material particle possesses a wavelength determined by its momentum. A slowly moving particle has a longer wavelength, while a particle with greater momentum has a shorter one. For everyday objects, this wavelength is so tiny that wave effects are effectively unobservable. For electrons, it can be large enough to produce diffraction and interference. The idea soon received experimental support. In 1927, Clinton Davison and Lester Germer directed electrons towards a nickel crystal. Because its atoms were arranged regularly, the crystal acted as a diffraction structure. The scattered electrons appeared strongly at particular angles, matching the wavelength predicted by Louis de Broglie. Around the same period, George Paget Thomson passed electrons through thin metal foils and observed diffraction rings. His work independently confirmed that electrons, previously treated as ordinary particles, produced unmistakably wave-like patterns. There was a pleasing historical irony. Joseph John Thomson, the father of George Paget Thomson, had helped establish the electron as a particle. George Paget Thomson then demonstrated that the same electron also behaved like a wave. Physics occasionally develops a sense of humour, although it tends to express it through laboratory equipment. The puzzle becomes clearest when electrons or photons are sent through an interference experiment one at a time. Each arrival produces one localized mark on the detector. There is no faint fraction of an electron spread across the screen. One complete detection occurs in one place. At first, the marks appear scattered. As more particles arrive, however, the interference pattern gradually emerges. The final distribution contains bright and dark regions, as though each particle had been shaped by wave-like contributions associated with more than one possible route. A spread-out description predicts a point-like event. Repeated point-like events reveal the spread-out pattern. Wave-particle duality is sometimes described as though a quantum object changes costumes, becoming a wave when convenient and a particle when someone looks closely. That image is memorable, but misleading. An electron is not a miniature classical ball that briefly dissolves into a ripple before becoming solid again. The lesson is more fundamental. The classical categories themselves are inadequate. Quantum systems produce interference that cannot be explained by independent particles following definite classical paths, yet they are detected through discrete events that do not resemble a classical wave arriving smoothly across a screen. Physics therefore needed a new kind of state. It had to preserve amplitude, phase, diffraction, and interference, while also producing probabilities for individual outcomes. It had to describe several possibilities, without reducing them to ordinary ignorance about one hidden classical answer. That description would become the quantum wave function, carrying wave-like structure into a theory whose experiments always end with something definite. By the middle of the 1920s, the strange behaviour of light and matter had become impossible to ignore. Light could interfere like a wave, yet transfer energy in discrete packets. Electrons could arrive as localized impacts, yet diffract from crystals as though they possessed wavelengths. Physics had collected the evidence, but still lacked one mathematical language capable of describing it together. Erwin Schrödinger set out to build that language. He was inspired especially by Louis de Broglie, who had argued that material particles should be associated with waves. If electrons possessed wavelengths, Schrödinger reasoned, perhaps atoms could be understood through matter waves, rather than through tiny particles circling a nucleus along definite classical paths. Atoms displayed a puzzling combination of continuity and discreteness. An electron seemed capable of moving through space, yet atoms emitted and absorbed light only at specific energies. The spectrum of hydrogen contained sharply defined lines, rather than every colour being produced equally. Any successful theory had to explain why only certain atomic energies were allowed. In 1926, Schrödinger developed wave mechanics and introduced the equation that now carries his name. The Schrödinger equation describes how a non-relativistic quantum state changes through space and time. It does not treat the electron as a small planet travelling around an atomic sun. Instead, it assigns the system a wave function and provides a rule for how that wave function evolves. The mathematics can become elaborate, but its basic role is simple. The equation connects the way the wave function changes with the total energy of the system. That energy includes kinetic energy, associated with motion, and potential energy, associated with the forces and surroundings experienced by the particle. In ordinary mechanics, Newton's laws tell us how position and velocity change when forces act. In wave mechanics, the Schrödinger equation tells us how the wave function develops when the system has a particular arrangement of energy. Once the wave function is known at one moment, the equation determines its later form, at least until measurement enters. The hydrogen atom provided one of the first great tests. Hydrogen contains one electron bound to one proton, making it the simplest atom. Even so, the electron cannot be described correctly as following one narrow orbit around the nucleus. When this Schrödinger equation is solved for hydrogen, only certain stable wave patterns are permitted. These resemble the fixed standing wave patterns that form on a string. A string attached at both ends cannot support just any vibration. It settles into particular modes that fit the boundaries. In a similar mathematical sense, an electron bound within an atom can occupy only certain allowed wave function states. Each allowed state possesses a definite energy. The discreteness of atomic energy levels therefore emerges from the structure of the wave equation. The energies are not added as an arbitrary rule after the calculation. They appear because only particular wave patterns satisfy the conditions required for a physically acceptable solution. This was a profound achievement. Quantist energy levels could now be understood as natural features of matter waves. When an atom moves from one allowed state to another, the difference in energy can be emitted or absorbed as light with a corresponding frequency. The spectral lines of hydrogen became consequences of a deeper mathematical structure. The allowed wave function states of electrons and atoms are called atomic orbitals. The name can mislead because it sounds like orbit. An orbital, however, is not a path. It does not show where an electron travels as it loops around the nucleus. It is a quantum state with a particular energy, spatial structure, and set of measurable properties. Different orbitals can possess different shapes. Some are spherically symmetric around the nucleus. Others contain lobes or nodal regions where the probability of detecting the electron becomes very small or zero. These shapes reflect the structure of the wave function, not miniature tracks worn into space by a tirelessly circling electron. At first, Schrödinger hoped the wave function might describe a real, physically spread out wave of matter or electric charge. That offered a continuous picture. Instead of a particle jumping mysteriously between allowed orbits, perhaps the electron was an extended wave surrounding the nucleus. The difficulty was that electrons did not reveal themselves as diluted clouds of charge. Detectors registered complete localized events. An electron arriving at a screen produced one spot. In scattering experiments, charge and energy were transferred in discrete amounts. A wave that seemed spread across space somehow led to an indivisible detection at one location. Schrödinger's wave mechanics was not the only successful formulation of quantum theory. Werner Heisenberg had developed matrix mechanics, an approach focused on observable quantities and transitions between quantum states. Its mathematics looked very different from Schrödinger's continuous waves. At first, the two theories appeared almost unrelated. One used wave functions and differential equations. The other used arrays of quantities whose order of multiplication mattered. Yet Schrödinger demonstrated that the two approaches were mathematically equivalent. Paul Adrian, Maurice Dirac, and other physicists helped reveal the deeper structure connecting them and developed a more general language containing both. This equivalence showed that wave mechanics was not simply one picturesque model competing with another. Different mathematical representations could encode the same measurable predictions. The wave function was powerful, but its visual appearance could not automatically be treated as a literal photograph of reality. The Schrödinger equation remained central to physics. It accurately describes atoms, molecules, chemical bonds, interference, tunneling, and countless laboratory systems. It gives the rule for the smooth evolution of a quantum state and reproduces the energy structure of hydrogen with remarkable success. But the equation does not explain what the wave function is made from. It does not say whether the wave is a physical substance, a field of possibilities, a guide for particles, or a mathematical description of knowledge. It tells the wave function how to change. It does not tell us what in the world is doing the changing. The mathematics had arrived. The interpretation was still waiting. Erwin Schrödinger had created a wave equation capable of reproducing the allowed energy states of atoms. What remained unclear was how this wave connected to the definite events recorded in experiments. A wave function could spread across many possible positions. A detector, however, responded in one place. A scattering experiment produced one particular deflection. An electron did not arrive as a pale fraction of itself distributed across an entire screen. In 1926, Max Born proposed the interpretation that provided the missing connection. He suggested that the wave function should not usually be understood as a literal distribution of matter or electric charge. Instead, it should be used to calculate the probabilities of different experimental outcomes. Born developed this idea while studying quantum scattering. Rather than focusing on an electron bound within an atom, he considered particles approaching a target and being redirected in different possible directions. Schrödinger's wave mechanics produced a pattern of outgoing waves, but an actual experiment would detect each scattered particle at one particular angle. The extended wave therefore seemed to describe a range of possible results, rather than a substance divided among them. Born recognized that the strength of the wave in a given direction could be connected to how frequently particles would be detected there over many repetitions of the experiment. The connection was not quite as simple as treating the wave function itself as an ordinary probability distribution. A classical probability must be a non-negative real number. A probability of less than 0 would not merely be unusual, it would be meaningless. One cannot have a negative chance of finding an electron behind a detector, however inconvenient the electron may be feeling. A wave function amplitude can behave very differently. It may be positive or negative, and it can also contain complex numbers. Complex numbers include a component involving the square root of -1. Although that sounds abstract, they are mathematically essential because they allow the wave function to carry phase information and evolve consistently through time. The wave function itself, therefore, cannot be read directly as a probability. Instead, Born connected probability to its squared magnitude. In clear language, the Born rule says that the probability of obtaining a result within a particular range is determined by the squared magnitude of the corresponding wave function amplitude. For position, this means that regions with a larger squared magnitude are more likely to contain the particle when its position is measured. Regions where the wave function has 0 amplitude have 0 probability of producing a detection. The rule does not normally predict the exact location of one individual event. It predicts the distribution that emerges when the same preparation and measurement are repeated many times. This distinction becomes especially important in the double-slit experiment. Suppose a quantum particle can reach a detector through either of two open slits. The wave function assigns a probability amplitude to the route through the first slit and another amplitude to the route through the second. These amplitudes are not probabilities by themselves. The amplitudes must first be combined. Only after they have been added is the squared magnitude calculated to obtain the final detection probability. This order matters enormously, because amplitudes carry signs and phases they can reinforce or cancel one another. At some points on the detector, the two contributions arrive with matching phases. Their amplitudes combine constructively, creating a larger probability of detection. At other points, their phases oppose one another. The amplitudes partially or completely cancel, reducing the probability or making it effectively zero. If ordinary probabilities were assigned separately to the two slits and then added, no interference pattern would appear. Probabilities cannot normally cancel one another. Probability amplitudes can. The dark bands in an interference pattern are therefore not places where particles simply happen to arrive less often by coincidence. They are regions where the quantum amplitudes associated with different possibilities cancel before probabilities are produced. This gives quantum probability a character unlike ordinary uncertainty. Imagine drawing one card from a shuffled pack and placing it face down on a table. The card already has a definite identity. It may be the Queen of Hearts or the Seven of Clubs. A person who has not looked simply lacks information. The probability describes ignorance about a fact that is already settled. In standard quantum mechanics, the situation is not generally treated in this classical way. Before a position measurement, the theory does not usually assign the electron one definite but unknown position. Before a spin measurement along a chosen direction, it does not necessarily assign one pre-existing result merely waiting to be uncovered. Instead, the wave function provides amplitudes for the possible outcomes. The act of measurement produces one of those outcomes with probabilities determined by the Born rule. This does not automatically prove that properties never exist before measurement. Different interpretations make different claims. Pilot wave theory, for example, assigns particles definite positions. Other interpretations treat outcomes as relative, branching, or genuinely created through measurement. The important point is that the standard formalism itself does not simply behave like classical probability over hidden, definite answers. For the probabilities to make sense, the wave function must also be normalized. Normalization means that all mutually exclusive possible results together must have a total probability of 1. If an electron is measured somewhere, then the probabilities for all possible locations must add to certainty. The electron may be found near one point, far from it, or somewhere in between, but the complete collection of possibilities must account for the whole experiment. Normalization can be imagined as distributing a total amount of probability across every allowed outcome. The distribution may change as the wave function evolves. It may spread, narrow, or form interference patterns. Yet the total probability remains 1, provided the system evolves according to the ordinary Schrödinger equation. Born's interpretation transformed wave mechanics into a practical predictive theory. Schrödinger's equation determined how the wave function changed. Born's rule explained how to turn that wave function into experimentally testable probabilities. Together, they allowed physicists to calculate atomic transitions, scattering angles, detection locations, and countless other outcomes. Repeated experiments confirmed the predicted distributions with remarkable accuracy. Yet the success came with a philosophical cost. If the wave function gives probabilities, what is it a wave of? Is it a real physical structure that determines the chances of different events? Does it describe incomplete information about a deeper state of reality? Is it merely a mathematical device for organizing expectations? Or does it represent something for which ordinary words such as physical and informational are both too limited? Born's interpretations solved the immediate experimental problem without resolving the deeper ontological one. It explained how the wave function connects to observed frequencies, but not whether the wave function itself exists independently in nature. Max Born later received the Nobel Prize in Physics for his fundamental contributions to quantum mechanics, especially his statistical interpretation of the wave function. By then, the rule bearing his name had become indispensable. The wave was no longer required to be a cloud of matter, it had become a source of probabilities. But probability did not make the mystery disappear, it simply gave the mystery numbers. A quantum state is the most complete description that standard quantum mechanics provides for a physical system. It contains everything the theory allows physicists to use when calculating the probabilities of every measurement that could be performed on that system. For a single electron, those measurements might concern position, momentum, energy, or spin. For an atom, they may include its allowed energy levels or the likelihood of emitting a photon. For a larger system, the state must describe all the possible configurations and correlations that matter to the experiment. The wave function is one way of representing that quantum state. It does not usually assign one ordinary number to the particle. Instead, it assigns a probability amplitude to each possible configuration within a chosen description. These amplitudes are complex valued, meaning that they contain both a magnitude and a phase. If position is being used, the wave function assigns an amplitude to every possible location where the particle could be detected. If momentum is used instead, it assigns amplitudes to different possible momenta. The same principle applies to energy levels, directions of spin, and other measurable quantities. These different descriptions are called bases. A basis is a chosen set of possible states used to express the quantum state. It is a little like describing the same location using different coordinate systems. The numbers may change when the description changes, but the underlying physical situation does not. A position wave function and a momentum wave function are therefore not two independent waves attached to the same particle. They are alternative representations of the same quantum state. One emphasizes the amplitudes associated with possible positions. The other emphasizes the amplitudes associated with possible momenta. The two are mathematically connected. Information that is sharply concentrated in one representation tends to be spread out in the other. This relationship is one of the structures behind the uncertainty principle. The amplitude assigned to a possibility carries two important features. The first is its magnitude. According to the Born rule, the squared magnitude determines the probability of obtaining the corresponding result when a measurement is made. The second feature is phase. Phase is harder to visualize because it is not itself an ordinary probability. It describes the position of an amplitude within a mathematical cycle. Two amplitudes may have similar magnitudes while possessing different phases, and those phase differences can alter how they combine. When amplitudes have matching phases, they can reinforce one another. When their phases oppose one another, they can partially or completely cancel. This is the source of quantum interference. The squared magnitude tells us how likely an outcome is after all relevant amplitudes have been combined. Relative phase determines how those amplitudes combine in the first place. This is why a wave function contains more information than a list of probabilities. Two quantum states can assign the same separate probabilities to certain alternatives while possessing different relative phases. When those alternatives are later recombined, the states can produce different interference patterns. A detector may therefore reveal consequences of phase, even though phase is not read from it as a simple number. Its effect appears through the distribution of outcomes. The wave function can also form what is called a wave packet. A single ideal wave with one perfectly defined wavelength extends endlessly through space. It is not concentrated around one particular region. Such a wave corresponds to a precisely defined momentum, but a completely indefinite position. A wave packet is created by combining many waves with different wavelengths and momenta. Their amplitudes reinforce one another within a limited region and cancel more strongly elsewhere, producing a state that is relatively localized. This localization comes with a cost. To build a narrow wave packet, many different wavelengths must be included. Because wavelength is related to momentum, a state confined to a small region must generally contain a spread of possible momenta. A broad packet can possess a relatively narrow momentum range. A tightly compressed packet requires a wider one. The particle cannot usually be represented by both a perfectly definite position and a perfectly definite momentum at the same time. Werner Heisenberg's uncertainty principle expresses this structural relationship. It is often described as though measuring equipment simply knocks the particle and spoils the answer. Measurement disturbance can occur, but that is not the fundamental point. The uncertainty principle is already present in the form of the quantum state before any measuring device is introduced. Position and momentum are represented by mathematical structures that do not allow both quantities to possess arbitrarily narrow probability distributions simultaneously. In natural language, the uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than a fixed limit determined by Planck's constant. This limit is extremely small on everyday scales, which is why a moving football can be treated as having both a well-defined position and a well-defined momentum. For an electron confined within an atom, however, the quantum limit becomes essential. Phase itself also contains an important distinction. Suppose every amplitude in an isolated wave function is multiplied by the same common phase. The mathematical expression changes, but all measurable probabilities remain exactly the same. This common factor is called a global phase. Because it affects every component equally, it produces no observable difference. Relative phase is different. If one component is shifted in phase while another is left unchanged, their interference changes. Regions that once showed constructive interference may become dark, while previously dark regions may become bright. Global phase is therefore physically irrelevant within ordinary quantum mechanics, while relative phase can have direct experimental consequences. This reveals something subtle about the information contained in a wave function. Not every mathematical feature written on the page corresponds to a separate observable property. Some features depend on the chosen representation, and some changes leave every possible measurement unchanged. Physicists therefore often regard quantum states that differ only by a global phase as representing the same physical state. Even so, the wave function remains an extremely rich description. It encodes probability amplitudes for possible results, phase relationships between alternatives, interference behavior, uncertainty relations, and correlations with other systems. Within standard quantum mechanics, a pure wave function is mathematically complete. If it is known exactly, the theory requires no additional variables to calculate the probabilities of any measurement. But mathematical completeness does not settle physical meaning. The wave function may be a literal part of nature. It may be a real structure evolving through a high-dimensional mathematical space. It may guide particles that possess additional properties. It may represent knowledge, expectation, or information about future experiences. It may describe relations between physical systems rather than an absolute state belonging to one object alone. Each interpretation can begin with the same amplitudes, phases, and probabilities, while telling a different story about what they represent. The wave function contains everything the standard theory needs for prediction. Whether it contains a picture of reality itself is a much harder question. For one isolated particle, the wave function can look almost reassuringly familiar. Imagine a single, spinless electron moving through otherwise empty space. Its position wave function assigns a complex, valued amplitude to every possible location in ordinary three-dimensional space. One amplitude corresponds to a possible position to the left, another to a point above, another to a point farther away, and so on throughout the region being considered. Because those amplitudes are spread across the same 3 dimensions in which the electron may be detected, it is tempting to picture the wave function as a physical cloud surrounding the particle. It may seem like an unusual version of an electromagnetic field, with a value at every point in space. That picture can be useful for simple systems, but it does not survive for very long. The difficulty appears as soon as a second particle is added. A complete position wave function for 2 particles must assign an amplitude to every possible combined arrangement of both particles. It does not merely need to describe where the first particle may be, it must also include where the second particle may be for every possible position of the first. Suppose the first particle could be located at one point in the room, while the second is near the window. That is one possible configuration. The first could instead be near the ceiling while the second is close to the floor. That is another. Every possible pairing of their positions requires its own probability amplitude. 3 coordinates are needed to specify the position of the first particle. Another 3 are needed for the second. The combined wave function therefore depends on 6 spatial coordinates. These 6 coordinates do not mean that either particle individually moves through 6 visible dimensions. Both are still detected within the same familiar 3-dimensional world. The higher dimensional description is required because the wave function represents their complete joint configuration. The mathematical arena containing all such possible arrangements is called configuration space. Ordinary physical space identifies possible locations of individual objects. Configuration space identifies possible arrangements of an entire system. Each point within it represents one complete configuration. For one particle, a point in configuration space can correspond to one position in physical space, so the distinction is easy to overlook. For 2 particles, one point in configuration space represents 2 positions at once. For 3 particles, it represents 3 positions. The number of dimensions rises quickly. A system containing 10 particles requires 30 spatial coordinates to describe one complete arrangement. Its position wave function therefore exists mathematically across a 30-dimensional configuration space, even before properties such as spin are included. 10 particles is hardly a large collection. A drop of water contains on the order of hundreds of sextillions of molecules. A macroscopic object contains vastly more particles still. Describing all of their possible positions through one wave function would require a configuration space with an almost incomprehensibly large number of dimensions. This does not mean physicists attempt to write down the exact universal wave function of every atom in a cup of tea before deciding whether it has cooled. Approximations, effective theories, and simplified models make practical calculations possible, but the underlying mathematical structure remains. For many particle quantum mechanics, the complete state is generally a function over configuration space rather than a set of independent waves floating separately through ordinary space. Entanglement makes this especially important. If 2 particles are not entangled, their total wave function may sometimes be separated into one wave function for the first particle and another for the second. In that special case, each particle can be given its own independent quantum state. An entangled state cannot be divided in this way. The amplitudes belong to the combined arrangements of both particles. The theory may assign a strong amplitude to one configuration in which the first particle has one property, and the second has a corresponding property, while assigning another amplitude to a different correlated configuration. Neither particle then possesses a complete independent wave function of its own. Only the combined system has one pure quantum state. This is not merely a complicated way of organizing information that physicists could discard with enough patience. Entanglement produces measurable correlations that cannot generally be reproduced by treating each particle as an isolated system carrying its own independent state. The global configuration space wave function therefore performs an essential role. It encodes relationships between particles that are not reducible to separate descriptions placed side by side. This creates one of the deepest problems for a straightforward realist interpretation of the wave function. If the wave function is a real physical object, where does that object exist? For one particle, the answer might appear simple. The wave exists across ordinary space. For two particles, however, the complete wave exists naturally across six-dimensional configuration space. For 10 particles, it belongs to 30 dimensions. For the contents of an ordinary room, the relevant number becomes fantastically larger. Some philosophers and physicists accept this conclusion. They argue that configuration space may be more fundamental than the three-dimensional world of everyday experience. On this view, the universal wave function is a real structure evolving within an enormously high-dimensional space. Chairs, planets, laboratories, and human beings would not be the most basic objects in nature. They would emerge as stable patterns within the universal wave function. Ordinary three-dimensional space would then be something like an effective structure, arising from deeper relationships encoded in configuration space. The world appears three-dimensional because certain patterns within the fundamental quantum state behave as objects arranged within three spatial dimensions. This proposal is sometimes called wave function realism or configuration space realism, although different advocates formulate it in different ways. It takes the mathematics seriously by treating the natural domain of the wave function as part of the fundamental ontology. The cost is substantial. The familiar world must somehow emerge from a space containing an extraordinary number of dimensions. A theory must explain why observers experience local objects in 3 dimensions rather than the full geometry of configuration space. Other interpretations reject the idea that the mathematical domain of the wave function must be a physical place. Configuration space may instead be an abstract space used to organize possible arrangements and calculate probabilities. A weather forecast can assign probabilities to many combinations of temperature, wind, and rainfall, without those combinations occupying a literal physical landscape. In a similar spirit, the wave function may encode possibilities without existing as a material wave inside its mathematical domain. Pilot wave theories may treat particles in ordinary space as physically fundamental, while also assigning the wave function a guiding role. Relational and informational interpretations may view the state as dependent on interactions, knowledge, or expectations rather than as a substance-filling configuration space. None of these positions has been established simply by observing interference or entanglement. The experiments confirm the mathematical structure and its predictions. They do not directly label configuration space as physical or abstract. The question therefore becomes more difficult than asking what medium carries the quantum wave. The wave function may not live in the space around us at all. It may inhabit a deeper configuration space, describe relations among possible arrangements, or exist only as part of the theory's mathematical machinery. And if it is physically real, then reality may be far larger than the 3 dimensions through which anything has ever appeared to move. Quantum mechanics allows physical possibilities to combine in a way that has no true classical equivalent. This feature is called the superposition principle, and it follows from the linear mathematical structure of the theory. If one wave function is a valid state of a system, and another wave function is also valid, then an appropriate combination of those states can form a new valid state. The system is not required to occupy only one of the original alternatives. It can be described by a superposition containing amplitudes associated with both. This sounds, at first, rather similar to ordinary uncertainty. A coin hidden beneath a cup might be heads or tails. A card drawn from a shuffled pack might be red or black. In each case, several possibilities can be listed because the answer is unknown. A quantum superposition is not merely a list of that kind. When a coin is covered, it still has one definite face pointing upward. The uncertainty belongs to the observer. The alternatives do not combine, reinforce, or cancel. No special pattern appears because the hidden possibility of heads has a different phase from the hidden possibility of tails. Quantum states are different because their components possess probability amplitudes. Each amplitude has both a magnitude and a phase. Those phases determine how the components behave when they are brought together within an experiment. A coherent superposition therefore contains relationships between possibilities. Its alternatives can interfere. The two-path experiment makes this distinction especially clear. A particle such as an electron is directed towards a barrier containing two narrow openings. Beyond the barrier is a detector capable of recording where the electron arrives. When both paths are available, the quantum state contains an amplitude associated with the first path and another amplitude associated with the second. The theory does not calculate the probability for each path separately and then simply add the two probabilities together. Instead, the amplitudes are combined first. In natural language, the total probability of detection is found by combining the amplitudes associated with all indistinguishable alternatives and then taking the squared magnitude of that combined amplitude. Because the amplitudes carry phase, their sum can be larger or smaller than either contribution alone. At some positions on the detector, the two-path amplitudes reinforce one another. At other positions, they cancel. This produces the alternating regions of high and low detection probability, recognized as an interference pattern. If ordinary classical probabilities were being added, opening a second path could only maintain or increase the chance of arrival at each point. It could not create a region where the particle becomes less likely to appear than it was with only one path open. Quantum interference can do exactly that. Adding an available route can reduce the probability of an outcome because the new amplitude may cancel the original one. Particles can be released through the apparatus individually. Each electron still produces one small localized mark on the detector. It does not spread itself thinly across the entire interference pattern, leaving a delicate fraction of charge in every bright region. One electron arrives in one place. At first, a small number of impacts may appear almost random. As hundreds, thousands, and eventually many more events accumulate, the interference pattern becomes visible. The distribution of individual points reflects the combined amplitudes associated with both paths. The wave function therefore predicts a spread of possible outcomes while every trial ends with one definite record. It is this marriage of extended amplitudes and localized events that makes superposition so difficult to translate into ordinary language. The pattern also depends on whether the two paths remain indistinguishable. Suppose a detector is placed near the opening so that the route taken by the electron can, in principle, be determined. It is tempting to say that interference disappears because someone has looked at the particle. That description gives human awareness far too much credit. Which path information is a physical correlation. If the electron passes through one opening, it may leave the path detector in one state. If it passes through the other, it may leave the detector in a distinguishably different state. The electron and the measuring device then become entangled. The total state no longer contains only an amplitude for the first path and an amplitude for the second. It contains one combined alternative involving the first path and the first detector record, together with another involving the second path and the second detector record. If those detector records are distinguishable, the path alternatives can no longer combine coherently within measurements of the electron alone. The interference terms are lost from the observed distribution. No person needs to read the detector. The information could be stored in a microscopic change, a scattered photon, or a vibration in the surrounding apparatus. Once the alternatives become physically correlated with distinguishable states elsewhere, interference in the chosen subsystem can disappear. The important issue is not human knowledge in the everyday sense. It is whether the physical world contains a record capable of distinguishing the alternatives. This also explains why simply avoiding a conscious observation does not restore interference. A detector left running in an empty laboratory still interacts with the electron. The universe is quite capable of keeping records without asking anyone to check the paperwork. Physicists often use a mathematical object called a density matrix to describe these situations more generally. A wave function is suitable for a pure quantum state, meaning a state with fully specified coherent amplitudes. A density matrix can represent both coherent superpositions and ordinary statistical mixtures. At a high level, the density matrix keeps track of the probabilities associated with different alternatives and also the coherence between them. The parts representing coherence contain the phase relationships that permit interference. For a coherent superposition, those relationships remain present. For an ordinary mixture, they are absent. Consider an experiment in which half the particles are deliberately sent through the first path and half through the second, with the choice made randomly. That produces a classical mixture. Each particle follows one prepared alternative, and the final pattern is the sum of the two separate distributions. Now compare this with a coherent superposition in which both path amplitudes are maintained. The separate probabilities may appear similar before the paths are recombined, but the coherent state can generate interference while the mixture cannot. This difference is experimentally observable. A coherent superposition and a classical mixture are therefore not two verbal descriptions of the same hidden situation. They make different predictions once the relevant alternatives are allowed to interact again. That fact sharpens the question of whether the wave function is real. It cannot be dismissed as a simple catalogue of possibilities, like a list of cards that might be hidden under a table. The relative phases encoded by the wave function influence measurable outcomes. This does not prove that the wave function is a material substance. An informational interpretation may still argue that it represents structured expectations rather than a physical wave. A realist interpretation may treat its coherent amplitudes as genuine features of nature. Other approaches may assign reality to particles, relations, branches, or measurement events. But any interpretation must account for the same fact. Quantum possibilities do not merely sit beside one another, they combine, interfere, and alter what can happen. The superposition principle gives possibilities a structure. The wave function carries that structure, and experiments reveal its effects one localized event at a time. The Schrödinger equation describes a remarkably orderly kind of change. Once the wave function of an isolated quantum system is known, the equation determines how that state develops through time. The evolution is smooth, continuous, and deterministic. Nothing in the equation itself selects one outcome from several possibilities. Measurement appears to introduce a different kind of event. Suppose an electron is prepared in a superposition of two possible spin results. Before measurement, the wave function contains an amplitude associated with each outcome. Under ordinary Schrödinger evolution, both components remain present and continue to evolve together. When the spin is measured, however, the apparatus records one definite result. The pointer indicates one direction, rather than displaying a blurred compromise between both. Repeating the experiment produces different individual outcomes, but their overall frequencies follow the probabilities predicted by the Born rule. The tension between these two descriptions is called the quantum measurement problem. On one side is smooth and deterministic wave function evolution. On the other is the appearance of one definite and apparently random result. The theory predicts the probabilities extremely well, but the relationship between these two kinds of change is not immediately clear. Textbook quantum mechanics often handles the situation by introducing the projection postulate, commonly called wave function collapse. According to this rule, a measurement replaces the original superposition with the state corresponding to the result that was observed. If the apparatus records one spin value, the wave function is projected onto the state associated with that value. The other possible outcome no longer appears in the post-measurement state. The probability of each collapse result is determined by the Born rule. This creates two apparently distinct forms of evolution. Between measurements, the wave function changes according to the Schrödinger equation. This evolution is unitary, meaning that it preserves the full quantum information and carries superpositions into later superpositions. During a textbook measurement, the state instead changes probabilistically and discontinuously. Several possible outcomes are replaced by one. The theory does not predict which individual result will occur, only the probability assigned to each. The central difficulty is not that the calculation fails. It is that the formalism seems to contain one rule for ordinary evolution and another for measurement, without clearly defining what makes an interaction count as a measurement. John von Neumann examined this problem mathematically by treating the measuring apparatus as a quantum system. Imagine an electron in a superposition of two possible states, and a detector initially displaying a neutral reading. When the electron interacts with the detector, the Schrödinger equation does not automatically force the pointer into one position. Instead, it produces an entangled state. One component contains the first electron result correlated with the first pointer position. Another contains the second electron result correlated with the second pointer position. The microscopic superposition has not disappeared. It has spread into the apparatus. This is sometimes called the von Neumann measurement chain. The electron becomes correlated with the detector. The detector may then become correlated with a computer, a printed record, the surrounding laboratory, and eventually an observer. If every part of this chain is governed by quantum mechanics, then the combined wave function contains several correlated alternatives. The mathematics alone does not obviously identify the precise moment when one result becomes uniquely real. Erwin Schrödinger exposed the discomfort through his famous cat thought experiment. A cat is placed in a sealed enclosure with a quantum event connected to a mechanism capable of releasing poison. If the event occurs, the cat dies. If it does not, the cat remains alive. When the quantum state contains both possibilities, applying the ordinary wave equation to the entire apparatus appears to create a superposition involving both a living cat and a dead cat. Schrödinger did not propose this as a practical method for placing household pets into mystical states. The thought experiment was designed to reveal the absurdity that seemed to arise when microscopic superpositions were extended without restriction into the everyday world. Real cats interact continuously with air molecules, thermal radiation, the container, and countless internal degrees of freedom. Visible interference between macroscopically different cat states would be destroyed almost unimaginably quickly. Even so, environmental interaction alone does not automatically explain why one outcome rather than the entire entangled state is experienced. The measurement chain also makes it difficult to draw a precise boundary. Does collapse occur when the electron reaches the detector, when the pointer moves, when a permanent record forms, when a human sees the result, or when information enters the surrounding environment? Moving the boundary farther along the chain does not remove the question. It merely relocates it. Popular accounts sometimes suggest that human consciousness performs the decisive act, as though reality remains unfinished until a person looks at it. Most modern approaches do not require this claim. A measuring device can register an outcome in an empty laboratory. A scattered photon can carry information into the environment. A chemical reaction can preserve a record long before any observer becomes aware of it. Human awareness may be part of the physical chain, but quantum mechanics does not usually require the mind to manufacture the external world by glancing at laboratory equipment. The universe managed to produce definite-looking events for billions of years before anyone arrived to take notes. The meaning of collapse depends strongly on what the wave function is believed to represent. If the wave function is physically real, collapse appears to be a dramatic physical transformation. A state spread across several possible configurations suddenly becomes concentrated on one outcome. If the alternatives are widely separated, the change may appear to occur across a large distance without any ordinary signal travelling between them. This raises difficult questions about what causes collapse, when it occurs, and whether it should be described by a new physical mechanism. If the wave function instead represents information or expectation, collapse can be understood differently. Learning a measurement result changes the probabilities that should be assigned to later outcomes. The wave function updates because the available information has changed. This resembles the revision of an ordinary probability distribution after new evidence arrives. Yet the analogy is not perfect, because quantum amplitudes carry phase and produce interference rather than behaving like simple classical uncertainty. Other interpretations remove collapse, modify it, or relocate its meaning. The many-worlds interpretation retains the complete wave function and treats the different outcomes as decohered branches. Pilot wave theory gives particles definite configurations while the guiding wave evolves continuously. Objective collapse theories add a real stochastic reduction process. Relational quantum mechanics describes outcomes relative to interacting systems. These approaches may agree on the observable probabilities of ordinary experiments, while disagreeing profoundly about what happens during measurement. Accurate prediction alone cannot decide between theories that have been constructed to produce the same results. The laboratory record tells physicists what occurred. It does not automatically reveal whether the wave function physically collapsed, whether the observer became part of a branch, whether a hidden configuration selected the result, or whether the state merely changed as a description. Measurement, therefore, does more than reveal a quantum system. It exposes the gap between the formal rules of quantum mechanics and the stories physicists tell about reality. The calculation ends with one answer. The meaning of that answer remains unsettled. A quantum system is rarely as isolated as the equations first suggest. An electron in a laboratory may interact with stray photons. A molecule may collide with surrounding gas. A measuring device may exchange heat with the room, vibrate internally, or scatter light into the environment. These interactions matter because quantum coherence is delicate. Environmental decoherence is the process by which a quantum system becomes entangled with its surroundings, causing the phase relationships between different components of its wave function to become effectively inaccessible. The foundations of this idea were developed especially through the work of Heinz-Dieter Z, and later expanded by Wojciech Zurek and many other physicists. Imagine a particle prepared in a superposition of two possible positions. If the particle were perfectly isolated, the amplitudes associated with those positions could remain coherent. Their relative phase could later be revealed by allowing the alternatives to overlap and interfere. In a realistic environment, however, the particle does not remain alone. A photon may scatter from it differently depending on which position it occupies. An air molecule may collide with one possible location rather than the other. Each interaction carries away some information about the alternatives. The system then becomes entangled with its environment. One part of the total wave function may describe the particle in the first position, correlated with one state of the surrounding photons and molecules. Another part may describe the particle in the second position, correlated with a distinguishably different environmental state. The phase relationship has not necessarily vanished from the total quantum state. Instead, it has become distributed across an enormous web of correlations involving the system and its surroundings. Recovering the original interference would require controlling not only the particle, but also every relevant photon, molecule, vibration and thermal disturbance that has become correlated with it. For a macroscopic system, that task becomes practically impossible. Consider a tiny dust grain suspended in air. Even though it is microscopic by everyday standards, it contains an enormous number of atoms. Air molecules continually strike its surface, and photons from the walls, lamps and thermal radiation scatter from it. If the dust grain were somehow placed in a superposition of two visibly separated positions, the environment would begin recording which position was associated with each scattered particle of light or air. At ordinary temperatures and pressures, coherence between the two locations could be suppressed in a fantastically short time. The exact timescale depends on the size of the object, the separation between the alternatives, the surrounding temperature, and the density of the environment. For large objects in ordinary conditions, decoherence can occur vastly faster than any human response time, sometimes in a tiny fraction of a billionth of a second. This helps explain why tables, measuring pointers, and cups of tea do not display visible interference between several locations. They are not protected from the world. They are being continuously monitored, in a purely physical sense, by their environments. The same principle applies to measuring equipment. A pointer coupled to a quantum particle may initially become entangled with several possible outcomes. One component of the wave function contains the pointer indicating one result. Another contains it indicating a different result. The pointer then interacts with the surrounding air, light, internal vibrations, and laboratory equipment. Those interactions rapidly distribute information about its position into the environment. Interference between the different pointer states becomes effectively inaccessible. Physicists often describe the state of the observed system using a reduced density matrix. This is obtained conceptually by taking the complete quantum description of the system and environment, then ignoring the environmental details that are not being measured. The full state may remain a coherent entangled superposition. Once the environment is left out of the practical description, however, the reduced state can resemble an ordinary classical mixture. The different outcomes appear with probabilities, while the terms responsible for observable interference become extremely small. The system then behaves as though it had settled into one of several classical alternatives, even though the total wave function may still contain all the correlated components. This resemblance must be treated carefully. A reduced density matrix that looks like a classical mixture does not necessarily prove that one outcome has physically replaced the others. It explains why interference between them is no longer available to ordinary local measurements. Environmental interactions also favour particular kinds of stable quantum states. Wojciech called these pointer states. Pointer states are states that remain relatively robust while interacting with the environment. For a measuring device, they often correspond to definite pointer positions. For larger objects, relatively localized positions are commonly stable, because the environment continuously becomes correlated with where the object is. A delicate superposition of widely separated positions is rapidly disrupted, while a reasonably localized position leaves a more consistent record in surrounding photons and particles. The environment therefore selects certain states as especially resistant to decoherence. This process is sometimes called environment-induced superselection. It helps explain why the classical world appears to contain objects with stable positions and measuring devices with readable results rather than persistent visible combinations of incompatible alternatives. Decoherence successfully explains several major features of the quantum to classical transition. It explains why interference becomes difficult to observe in large open systems. It explains why records are robust and can be copied into many parts of the environment. It also explains why classical descriptions work so well for objects that are constantly interacting with their surroundings. What decoherence does not settle unanimously is why one unique outcome is experienced. The total wave function of the system and environment may continue to contain several decohered components. One includes one result and its environmental record. Another includes a different result and a different record. Decoherence explains why those components no longer interfere appreciably, but it does not by itself select one and delete all the others. Different interpretations respond to this remaining question in different ways. Everettian interpretations treat the decohered components as effectively independent branches of the universal wave function. Each branch contains a definite-looking outcome relative to the observer within it. Objective collapse theories accept decoherence, but add a genuine physical reduction process that eventually removes all but one alternative. Pilot wave theory uses decoherence to explain why different parts of the guiding wave cease to influence the actual particle configuration in ordinary circumstances. Informational and epistemic interpretations may treat the reduced state as the appropriate description for an observer who lacks access to the environmental correlations. The apparent change reflects both physical interaction and a change in the predictions that can reasonably be made. Decoherence therefore reveals that quantum coherence has real experimental consequences. Its preservation allows interference, while its dispersal into the environment makes quantum alternatives appear classical and separate. But this does not settle whether the wave function is a fundamental physical object. The same decoherence mathematics can be placed inside several incompatible pictures of reality. Quantum waves become hidden not because they simply disappear, but because their phase information becomes woven into the surrounding world. The pattern remains within the total description. It is merely scattered almost everywhere. The phrase Copenhagen interpretation sounds as though quantum mechanics received one official philosophical explanation, neatly agreed upon in a single room. The reality is less tidy. What is called the Copenhagen interpretation is better understood as a family of related approaches that developed around the early quantum research community, especially through the work of Niels Bohr, Werner Heisenberg, Max Born, and their collaborators. They shared several important ideas, but they did not always express them in exactly the same way. At the center of these approaches was a reluctance to force quantum phenomena into the familiar pictures of classical physics. Niels Bohr argued that quantum experiments could reveal different, mutually exclusive aspects of a system depending on how the experiment was arranged. He called this principle complementarity. The double-slit experiment provides the clearest example. When an apparatus is arranged to preserve interference, the particle is described through wave-like amplitudes associated with both paths. When the apparatus is arranged to determine which path was taken, the interference disappears and path information becomes available. These are not simply two incomplete photographs waiting to be combined into one classical picture. The experimental arrangements are incompatible. One reveals interference, the other reveals distinguishable paths. According to Bohr, both descriptions are necessary for a complete account of quantum phenomena, even though they cannot be applied simultaneously in the same experimental context. Complementarity, therefore, does not mean that the particle secretly possesses every classical property at once, and that physicists merely choose which one to inspect. It means that concepts such as path, position, momentum, and interference acquire meaning within particular arrangements of preparation and measurement. This shifts attention away from asking what the particle is doing in complete isolation between observations. In classical mechanics, it seems natural to imagine a planet following a definite orbit, even when no one is looking. Its position and velocity belong to it independently of the measuring equipment. The experiment merely reveals properties that already exist. The Copenhagen family treats the quantum situation more cautiously. The outcome cannot always be separated cleanly from the conditions under which it is measured. A statement about the particle must include the experimental context that makes the statement meaningful. This does not mean that the laboratory creates the entire universe out of nothing. It means that quantum theory may not support one observer-independent mechanical story in which every measurable quantity possesses a definite value at every moment. Bohr also insisted that experimental apparatus and recorded results must be described in classical language. This requirement can sound contradictory. If everything is ultimately quantum, why should a detector or measuring device be spoken of classically? Bohr's answer was practical and conceptual. Experiments must produce definite records that can be communicated. A pointer must indicate a readable position. A photographic plate must contain a visible mark. A counter must register one result rather than an ambiguous superposition of several spoken answers. Classical language provides the shared framework needed to specify what was prepared, how the apparatus was arranged, and what outcome was observed. Without that stable language, physicists could not compare results or even state clearly what experiment had been performed. The boundary between quantum system and classical apparatus was not necessarily presented as one permanently fixed physical division. It depended on the purpose of the experiment. A measuring device could itself be studied quantum mechanically in another context, while still being treated classically when it served as the instrument recording a result. This flexibility was useful, although it also left critics asking exactly where the quantum description should end. Different versions of the Copenhagen interpretation give the wave function different levels of significance. A strongly instrumental reading treats the wave function primarily as a tool for calculating the probabilities of measurement outcomes. On this view, asking what the wave function is physically made from may be considered unnecessary or even badly posed. The formalism connects preparations with possible results, and that is its proper task. More cautious Copenhagen approaches do not always declare that the wave function is merely subjective knowledge. Instead, they resist assigning it the status of a classical physical object. The wave function may provide the most complete quantum description available within a given experimental context, without being a material wave spread through ordinary space. It may encode objective possibilities or probabilities while still failing to represent a tiny mechanism operating behind the observations. This restraint is important. Copenhagen thinking is often reduced to the statement that nothing exists until it is observed. That slogan is far stronger and less precise than the historical views it is meant to summarize. Bohr did not simply claim that human consciousness conjures particles into existence. His emphasis was on the inseparability of quantum phenomena from the complete experimental conditions under which definite outcomes are obtained. Collapse can also be interpreted differently within this family of views. If the wave function is treated as a physical substance, collapse sounds like a wave suddenly contracting across space when a result is recorded. That image immediately raises questions about how fast the collapse travels and what physical force causes it. A Copenhagen-style account may instead regard collapse as a change in the description after measurement. Before the result is known, the wave function assigns amplitudes to several possible outcomes. After one outcome is recorded, the state used for future predictions is updated to reflect the new experimental situation. The collapse is then not necessarily a material wave crashing inward. It is a transition from one probabilistic description to another after a definite result has entered the record. This approach works extremely well in practice. A physicist prepares a state, calculates the possible outcomes, performs a measurement, updates the state, and continues. The predictions agree with experiment, often to remarkable precision. For many working researchers, this is enough. The attitude is sometimes summarized by the instruction to calculate the predictions and avoid worrying too much about interpretation. The exact wording has been attached to several physicists and should not be treated as one formal principle, but the general habit is real. Quantum mechanics is an extraordinarily effective working theory. A researcher designing a laser or calculating an atomic transition does not always need to decide whether the universal wave function is a real object living in configuration space. That practical success, however, does not remove the philosophical question. Avoiding an ontological claim is not the same as answering it. Treating the wave function as a predictive tool does not prove that it lacks physical reality. Refusing to describe what happens between measurements does not establish that nothing happens there. The Copenhagen family helped physicists use quantum mechanics without demanding an impossible classical picture. It emphasized experimental context, complementarity, classical records, and restraint when speaking about unobserved reality. But that restraint also preserved the central disagreement. The wave function could be indispensable without being declared a material object. Collapse could be an update without being identified as a physical process. Quantum theory could remain complete for prediction, while leaving its ontology deliberately unsettled. Copenhagen did not prove that the wave function is unreal. It taught physicists how to succeed without deciding. Not every interpretation of quantum mechanics gives up on definite particles. Pilot wave theory takes a very different approach. It keeps particles as real objects with exact positions, while also treating the wave function as a physically meaningful part of the theory. Rather than choosing between particles and waves, it assigns each a separate role. The idea began with Louis de Broglie during the 1920s. He had already proposed that particles such as electrons possess wavelengths related to their momentum. He then developed a deeper picture in which a particle follows a definite path while being guided by an accompanying wave. Louis de Broglie presented this pilot wave approach at the 5th Solvay Conference in 1927. At the time, however, the Copenhagen family of interpretations became far more influential. The pilot wave idea remained largely neglected until David Bohm independently revived and developed it in 1952. The resulting framework is now commonly called de Broglie-Bohm theory, Bohmian mechanics, or pilot wave theory. In this theory, a particle always has an actual position. An electron is never literally spread across several locations in the same sense as its wave function. It occupies one point in physical space and follows one continuous trajectory through time. The wave function evolves according to the ordinary Schrödinger equation. Alongside that evolution, a separate guiding rule determines how the particle moves. In verbal terms, the velocity of each particle is determined by the phase structure of the wave function at the actual configuration occupied by the system. The magnitude of the wave function remains important for statistical predictions, while its phase helps determine the direction and speed of the particle's motion. The wave does not push the particle through an ordinary mechanical force in the same way that wind pushes a leaf. Instead, the wave function guides the possible geometry of the trajectory. The double-slit experiment provides the most familiar example. An electron approaches a barrier containing two open slits. According to pilot wave theory, the electron itself passes through one slit and only one. It has a definite location at every instant, so there is no moment when the particle is literally divided into two pieces. The guiding wave behaves differently. The wave function extends through both available slits. The two parts of the wave emerge on the far side and interfere, creating a complex pattern of phase and amplitude. The electron's path is then guided by this interference structure. Depending on its initial position and the form of the wave, it curves towards one region of the detector rather than another. Each electron still produces one localized impact. Yet when the experiment is repeated with many similarly prepared electrons, their trajectories collectively form the familiar interference pattern. This allows pilot wave theory to tell a clear mechanical story. The particle goes through one slit. The wave goes through both. The interference belongs to the wave, while the individual impact belongs to the particle. If a witch-path detector is introduced, the wave function becomes entangled with the measuring apparatus. The effective guiding structure changes, and the ordinary interference pattern disappears. Human consciousness plays no special role. The result follows from physical interaction between the electron, the detector, and the surrounding environment. At the fundamental level, the theory is deterministic. Once the initial wave function and the exact starting configuration of all particles are specified, their later motion is fixed by the Schrödinger equation and the guiding equation. There is no fundamental random collapse selecting one outcome from several. The probabilities of ordinary quantum mechanics arise because the precise initial positions of particles are not known in practice. Pilot wave theory introduces the condition known as quantum equilibrium. In an ensemble of similarly prepared systems, particle configurations are distributed according to the squared magnitude of the wave function. In natural language, the probability of finding a particle within a region matches the squared magnitude of the wave function across that region. If this distribution holds initially, the dynamics preserve it over time. As a result, pilot wave theory reproduces the same Born rule statistics as standard quantum mechanics for ordinary experiments. A single particle follows one definite path, but researchers generally cannot know its exact starting position. Repeated trials therefore produce probabilistic distributions even though the underlying motion is deterministic. This resembles classical statistical mechanics in one respect. The motion of gas molecules may be deterministic even when their precise positions and velocities are unknown. Yet the pilot wave case is not simply classical mechanics with hidden details added. The guiding wave has a distinctly quantum structure, including superposition, phase, entanglement, and interference. Entanglement also makes the theory explicitly non-local. For several entangled particles, the wave function belongs to their combined configuration. The velocity of one particle can depend on the actual positions of other particles, even when those particles are widely separated. This does not normally permit controllable messages to travel faster than light. The observable predictions remain consistent with the no-signaling structure of quantum mechanics. Even so, the underlying theory contains instantaneous dependence across distance. John Stuart Bell showed that no theory based entirely on local hidden variables can reproduce all the statistical predictions of quantum mechanics. Experiments testing Bell inequalities have repeatedly supported the quantum predictions and ruled out broad classes of local explanations. Pilot wave theory accepts the lesson directly. Its hidden variable structure is non-local rather than local. For some physicists, this honesty is a strength. The theory does not attempt to preserve a classical idea of independent distant objects, when entanglement experiments indicate that such locality cannot be maintained in a straightforward way. For others, the non-locality remains conceptually uncomfortable, particularly when combined with Albert Einstein's special theory of relativity. Constructing fully relativistic pilot wave theories is possible in several forms, but it is more difficult than applying the theory to ordinary non-relativistic particles. The location of the guiding wave raises another challenge. For one particle, the wave function can be represented across ordinary three-dimensional space. For many particles, however, it naturally lives in configuration space. A two-particle wave function depends on 6 spatial coordinates. A 10-particle system requires 30. The real particles remain located within familiar three-dimensional space, while the guiding wave is defined over the combined configuration space of the entire system. If the wave function is physically real, what kind of reality does this high-dimensional object possess? Is configuration space a fundamental physical arena? Is the wave function more like a law governing particles than a material field? Or can it somehow be represented through interconnected structures within ordinary space? Supporters of pilot wave theory do not all answer these questions in the same way. Some treat the wave function as a genuine physical field in configuration space. Others regard it as nomological, meaning that it acts more like a law of motion than like matter or energy. Despite these disagreements, pilot wave theory establishes an important point. Quantum predictions do not force physicists to abandon definite particles or continuous trajectories. A coherent alternative exists in which particles always occupy real positions, and the wave function guides their motion. The cost is an explicitly non-local theory, and a wave function whose natural home may be a vast configuration space. Pilot wave theory is therefore not merely a historical curiosity. It is a complete and serious formulation of non-relativistic quantum mechanics, capable of reproducing the standard experimental predictions while offering a radically different account of what exists. The particles are real. The guiding wave may be real as well. The mystery simply moves from whether anything has a position to what kind of object could guide every position at once. Hugh Everett III proposed one of the most radical responses to the measurement problem in 1957. His original idea was called the relative state formulation of quantum mechanics. It later developed into a family of views now commonly known as the Everett interpretation or the many worlds interpretation. The central proposal is surprisingly simple. The wave function never collapses. There is only one fundamental rule of motion. The universal wave function always evolves according to the Schrödinger equation, smoothly and continuously, whether it is describing an electron, a measuring device, a human observer, or the universe as a whole. In textbook quantum mechanics, measurement appears to interrupt this evolution. A superposition of possible outcomes is replaced by one definite result through collapse. Everett removed that second process entirely. Measurement becomes an ordinary physical interaction governed by the same quantum dynamics as everything else. Imagine an electron prepared in a superposition of two possible spin results. A measuring apparatus begins in a neutral state, ready to record either outcome. When the electron interacts with the apparatus, the two systems become entangled. One component of the resulting wave function contains the electron, with the first spin result, and the apparatus displaying the corresponding reading. Another component contains the second spin result and a different apparatus reading. If an observer then looks at the apparatus, the observer also becomes correlated with those alternatives. One component contains an observer seeing the first result. Another contains an observer seeing the second. No unique outcome has been selected across the entire universal wave function. Instead, each observer state is correlated with one definite record. From within either component, the result appears completely ordinary. The observer sees one reading, remembers one event, and finds no awareness of the alternative. The other outcome belongs to a different component of the wave function containing a correspondingly different observer. Environmental decoherence then makes these components effectively independent. As the measuring apparatus interacts with photons, air molecules, thermal radiation, and the wider laboratory, information about each result becomes copied into the surrounding environment. The relative phase between the alternatives becomes dispersed across an enormous number of environmental correlations. Under ordinary conditions, the resulting structures no longer produce observable interference with one another. Each contains a stable record and behaves approximately like a classical world. These structures are commonly called branches. Popular explanations often describe the universe as suddenly splitting into several new universes whenever a measurement occurs. That picture is vivid, but it is only a rough metaphor. The formal theory contains one continuously evolving universal wave function. Branching refers to the development of effectively independent patterns within that wave function as entanglement and decoherence spread. There may be no precise instant at which one world cleanly divides into two. Decoherence is gradual, and the number of branches may not always be sharply defined. The important point is that different outcome records become dynamically isolated enough to behave as separate histories. In this interpretation, the wave function is not merely a tool for predicting reality. It is reality at the most fundamental level. Particles, measuring devices, planets, people, and apparently classical worlds are understood as stable structures or patterns within the universal wave function. The familiar three-dimensional world is not added separately to the theory. It is expected to emerge from the organization of the quantum state, and the way decoherence produces branch-like structures. This makes the Everett interpretation one of the strongest forms of wave function realism. The wave function is not simply knowledge about hidden particles, or a temporary description awaiting measurement. It is the complete physical state of the universe. The attraction of this view is mathematical economy. There is no special collapse law, no arbitrary boundary between quantum systems and classical apparatus, and no need to specify exactly when measurement occurs. Everything follows from the Schrödinger equation, entanglement, and decoherence. The conceptual cost is equally striking. If the universal wave function contains every outcome with non-zero amplitude, then reality includes a vast multiplicity of branch relative histories. Every ordinary quantum measurement creates correlations in which the different allowed results occur within different branches. This immediately raises a difficult question about probability. In a collapse theory, probability appears naturally because only one outcome will occur, and the Born rule assigns the chances. In the Everett interpretation, all allowed outcomes occur somewhere within the wave function. Why then should an observer expect one result rather than another? Why should branches be weighted according to the squared magnitude of their amplitudes? And what can probability mean when no allowed outcome is completely excluded from reality? Supporters have developed several responses. David Deutsch and later David Wallace used ideas from decision theory. They argued that a rational observer who knows the universal wave function but does not yet know which future branch they will experience should make decisions, as though branch weights follow the Born rule. Other approaches appeal to self-locating uncertainty. Before observing the result, a person may know that several future versions will exist but remain uncertain about which branch. Relative experience will become theirs. Some physicists argue that the statistical structure of repeated measurements naturally produces branches in which observed frequencies closely match the Born rule, with branches showing very different frequencies carrying extremely small total weight. These arguments are sophisticated, but their status remains debated. Critics question whether probability has been genuinely derived or quietly assumed through the meaning assigned to branch weight, rationality, or uncertainty. The interpretation must also explain how familiar objects emerge from a wave function defined over configuration space. It must identify the stable patterns corresponding to worlds, observers, and records without inserting classical reality by hand. Decoherence provides much of this structure, but debates continue over whether it defines branches precisely enough, and whether those branches deserve to be called separate worlds. The many worlds interpretation therefore makes clear trade. It removes collapse and preserves one simple universal law of quantum evolution. In return, it asks that the entire wave function be taken seriously, including every decohered outcome it contains. Nothing is randomly removed from the state. Nothing chooses one result for the universe as a whole. The wave function continues, carrying every branch with it. For Everettian quantum mechanics, asking whether the wave function is real receives the strongest answer available. It is not merely part of reality. It is the thing from which all apparent realities emerge. Objective collapse theories take the most direct possible approach to the measurement problem. Rather than treating collapse as a vague rule added whenever a measurement occurs, they propose that wave function reduction is a real physical process built into nature. In ordinary quantum mechanics, the Schrödinger equation allows a superposition to continue evolving smoothly. Collapse is then introduced separately to explain why one definite outcome appears. Objective collapse theories modify that basic dynamics so that sufficiently extended superpositions eventually become localized on their own. Measurement does not need to be fundamental. Consciousness does not need to intervene. A measuring device produces a definite record because the physical state genuinely collapses. One influential model was developed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber during the 1980s. Their proposal is often known by the initials of their surnames, but its basic idea can be stated without shorthand. Every microscopic constituent undergoes an extremely rare spontaneous localization. Most of the time, an isolated particle follows ordinary Schrödinger evolution. At unpredictable moments, however, its wave function becomes sharply concentrated around one position. For a single particle, the proposed localization rate is extraordinarily low. A microscopic superposition could therefore remain intact for a very long time. This allows electrons, atoms, and small molecules to display the interference required by experiments. The situation changes when enormous numbers of particles are bound together inside a macroscopic object. A measuring pointer may contain roughly a billion particles. Even if each constituent has only a tiny individual chance of localizing, the combined chance that some localization affects the object becomes very large. One event can then suppress the widely separated components of the entire entangled state. This amplification mechanism allows microscopic superpositions to survive while macroscopic objects rapidly acquire definite positions. A single atom may remain delocalized. a table does not quietly spread across the room while everyone is making tea. In this picture, the distinction between quantum and classical behaviour is not imposed by an observer. It emerges from the number of particles involved and the frequency of spontaneous localization. The original model describes collapse through rare, abrupt events. Philip Pearl developed a related approach known as continuous spontaneous localization. Instead of isolated jumps occurring at scattered moments, the wave function is subjected to a continuous random influence that gradually drives it towards a more localized state. The randomness is fundamental. It does not arise merely because hidden details are unknown. The theory itself contains stochastic, meaning genuinely probabilistic, modifications to ordinary quantum evolution. The larger and more massive the system becomes, the stronger the effective localization tends to be. Microscopic states can remain coherent, while macroscopic superpositions are steadily suppressed. Roger Penrose has suggested a different possible source of collapse involving gravity. A mass in two locations would correspond, according to general relativity, to two different arrangements of space-time geometry. Roger Penrose has argued that nature may be unable to sustain such competing geometries indefinitely. The greater the difference between the mass distributions, the shorter the lifetime of the superposition may become. This proposal is conceptually striking because it connects the measurement problem with the unresolved relationship between quantum mechanics and gravity. It remains speculative, however. No confirmed experiment has established that gravitational instability causes wave function collapse, and different mathematical versions of the idea remain under investigation. Objective collapse theories almost always treat the wave function as physically real. If collapse is an actual event, then something real must undergo that event. The wave function is not merely an observer's expectation changing after new information arrives. Its shape genuinely alters. A state spread across several possible regions becomes physically concentrated around one of them. That commitment gives collapse models an important advantage over many interpretations. They can produce predictions that differ, at least slightly, from standard quantum mechanics. This means they are not purely philosophical alternatives. They can be tested. Changing the Schrödinger equation can have small physical consequences. Depending on the model, spontaneous localization may inject tiny amounts of energy into matter. It may cause unexplained heating, weak radiation, or small disturbances in systems that should otherwise remain exceptionally quiet. These effects are expected to be extremely faint, but modern experiments can search for them. Matter wave interferometry tests whether increasingly large atoms, molecules, and clusters can remain in coherent superpositions. If interference persists where a collapse model predicts that localization should already have occurred, part of that model's parameter range can be ruled out. Optomechanical experiments attempt to place tiny mirrors, membranes, or mechanical resonators into quantum states. These systems occupy an interesting middle ground between individual particles and familiar macroscopic objects. Precision measurements can search for unexpected noise or heating in carefully isolated systems. Underground radiation experiments reduce interference from cosmic rays and natural background radiation, making it possible to look for faint emissions that certain collapse models might produce. The absence of such effects has placed increasingly strong constraints on the allowed collapse rate and localization scale. Some versions of the theories have become difficult to maintain, while others remain compatible with existing evidence. No confirmed objective collapse signal has yet shown that ordinary Schrödinger evolution fails. Quantum interference continues to appear in systems larger than the founders of quantum mechanics could easily have imagined. At the same time, experiments have not yet created and maintained a visible superposition of truly everyday objects under conditions capable of testing every proposed collapse mechanism. Objective collapse theories therefore remain open possibilities rather than established replacements for quantum mechanics. They offer a clear answer to the mystery of measurement. The wave function is real. Collapse is real. Definite outcomes arise because nature contains a small amount of fundamental randomness that destroys sufficiently large superpositions. The appeal is clarity. The cost is altering one of the most successful equations in physics and introducing effects that experiments have so far failed to confirm. If collapse theories are correct, then the wave function does not merely describe what might happen. It is a physical object that occasionally and unpredictably chooses one possibility for itself. The wave function may not be a physical object at all. To understand that possibility, it helps to separate two different kinds of description. An ontic state represents something that belongs to physical reality itself. An epistemic state represents knowledge, information, belief, or uncertainty about that reality. The distinction appears clearly in classical statistical mechanics. Imagine one molecule moving inside a sealed container. In principle, the molecule has one definite position and one definite velocity at each moment. A researcher may not know those values exactly, so they use a probability distribution to describe where the molecule is likely to be and how fast it may be moving. That probability distribution is epistemic. It reflects incomplete knowledge. The molecule itself is not physically spread across every location assigned a probability. It occupies one actual state, even if the observer does not know which one. This classical example makes an informational interpretation of the quantum wave function attractive. Perhaps a quantum system also possesses some deeper physical condition, while the wave function merely summarizes what can be known or expected about it. The amplitudes would then describe uncertainty rather than a literal wave moving through space or configuration space. Collapse would become easier to understand. If the wave function is physically real, measurement appears to cause a dramatic transformation. A state spread across several possible positions may suddenly become concentrated in one region. For entangled particles separated by a great distance, the description may change across the entire combined system at once. If the wave function represents information, collapse can instead resemble an update in expectations. Before a measurement, several outcomes are assigned probabilities. After one result is obtained, the observer revises the state used to predict future events. No physical substance needs to rush inward. The description changes because the available evidence has changed. This does not mean that quantum probabilities are identical to ordinary classical ignorance. Quantum amplitudes carry phase, interfere, and obey rules that classical probability distributions do not. An epistemic interpretation must still explain why information has this unusual structure. One of the most developed informational approaches is quantum Bayesianism, associated especially with Christopher Fuchs, Rudiger Schack, and Carlton Caves. The name combines quantum theory with Bayesian probability, a framework in which probabilities express an agent's degrees of belief about uncertain outcomes. In quantum Bayesianism, the probabilities derived from a wave function represent an agent's personal expectations concerning the consequences of actions performed upon the world. A measurement is treated as an action by an agent on a physical system. The outcome is the agent's resulting experience. The wave function organizes the probabilities that the agent assigns to those possible experiences. This is a strongly personal interpretation of the quantum state. Two agents with different information may legitimately assign different wave functions to the same external system. That does not mean quantum Bayesianism denies the existence of an outside world. It does not claim that atoms, detectors, or laboratories are imaginary. Instead, it denies that the wave function is an observer-independent physical property directly possessed by the system. Reality exists, but the quantum state expresses one agent's expectations about interacting with it. The Born rule then acquires a special role. It is not interpreted as a picture of a physical wave whose squared magnitude fills space with probability. Instead, it acts as a normative consistency relation. In simple terms, the Born rule tells an agent how different probability assignments must fit together if they are to be compatible with the structure of quantum theory. It links expectations about alternative possible actions and outcomes. The rule, therefore, guides rational probability assignments rather than describing a hidden material mechanism. The mathematics remains essential, but its role is closer to a disciplined framework for expectation than a map of an invisible substance. This approach removes some familiar puzzles while creating others. Collapse becomes an ordinary revision of belief after an experience. Different observers can assign different states without contradiction, because the wave function belongs to the agent's perspective. The measurement problem is softened because the theory is not required to explain how a real wave physically selects one branch. Yet critics ask what deeper physical structure produces the regularities captured so accurately by the Born rule. If the wave function belongs to the agent, what features belong to the system itself? Quantum Bayesianism deliberately leaves much of that underlying reality unspecified. A different contribution came from Robert Speckens, who developed a toy model based on restricted knowledge. In the model, a system possesses an underlying physical state, but an observer is never allowed complete access to it. The amount of knowledge available is limited by a rule stating, roughly, that what is known must be balanced by what remains unknown. From this restriction, the model reproduces several phenomena that resemble quantum behavior. It can display analogues of superposition, interference, indistinguishable states, measurement disturbance, and some forms of entanglement-like correlation. This is important because it shows that several apparently mysterious quantum effects can arise in a theory where probabilities represent incomplete knowledge about definite underlying states. The model does not reproduce all of quantum mechanics. It cannot account for the full range of non-local correlations revealed by experiments, and it does not provide a complete replacement for quantum theory. Its value is conceptual. It demonstrates that quantum-like behavior does not automatically prove that every feature of the wave function must be physically real. Interference remains one of the hardest challenges for epistemic interpretations. A classical probability distribution merely assigns weights to different hidden possibilities. Those probabilities do not carry relative phases, and they do not cancel one another. A quantum wave function contains phase relationships that influence measurable statistics. Two preparations may assign similar probabilities to separate outcomes, yet produce different interference patterns when their components are recombined. An informational account must therefore explain why a state of knowledge has precisely the mathematical structure required to generate these effects. Some interpretations answer by treating the wave function as objective information constrained by the physical preparation of the system. Others regard it as relative to an observer, an experimental context, or an interaction. Quantum Bayesianism treats it as personal probability, while other epistemic approaches allow a more observer-independent form of information. These views should not be grouped together too casually. They disagree about whose information the wave function represents, how subjective that information is, and what underlying reality remains beneath it. What they share is the rejection of one simple assumption. A mathematical object can be indispensable without being a material thing. The wave function may encode every probability needed for quantum prediction, while still describing knowledge, expectation, or accessible information rather than a physical wave. Informational interpretations therefore take the wave function completely seriously as part of quantum theory. They simply deny that using it successfully proves that it exists independently in the world. Perhaps the wave function does not describe a system by itself. That possibility lies at the center of relational quantum mechanics, an interpretation developed by Carlo Rovelli. In this view, the physical state of a quantum system is meaningful only relative to another physical system with which it interacts. A property such as position, spin, or energy is not always treated as an absolute possession carried by an object independently of everything else. Instead, it becomes definite in relation to another system through a physical interaction. This changes the meaning of measurement. Measurement is not a mysterious event requiring a conscious observer, nor does it demand a permanently classical apparatus standing outside quantum mechanics. It is simply an interaction in which two physical systems become correlated. One system might be an electron, the other might be a detector. When they interact, the detector acquires a definite record relative to the electron, while the electron acquires a definite measured value relative to the detector. No human mind is needed. A molecule can measure another molecule in this relational sense. A photon can interact with an atom. A dust grain can become correlated with surrounding light. The term observer refers to any physical system relative to which a property is defined. Imagine a quantum particle in a superposition of two possible spin values. A detector begins in a neutral state and then interacts with the particle. Relative to the detector, one definite result may be recorded. The pointer moves to one position, and the particle possesses the corresponding spin value in relation to that apparatus. Now imagine a third system that has not yet interacted with either the particle or the detector. From the perspective of this third system, the combined particle and detector may still be described by an entangled superposition containing both correlated possibilities. One description says that a definite outcome has occurred relative to the detector. Another says that the larger combined system remains in a superposition relative to the third system. Relational quantum mechanics does not treat these statements as contradictory. They refer to different physical relations. This is not the same as saying that reality is merely a matter of opinion. The detector cannot simply prefer one result because it likes the look of it. The relation is established by an actual interaction governed by quantum mechanics. Once the detector and particle interact, their correlation is physically real relative to one another. The result is not a private belief or an imagined possibility. It is a fact about the relation between those systems. What relational quantum mechanics rejects is the demand for one absolute description that assigns every property from a viewpoint outside all physical interactions. There may be no universal perspective from which every system possesses one simultaneously defined quantum state. The wave function assigned to an object depends on the system relative to which the description is made. A cautious comparison can be drawn with Albert Einstein's theory of relativity. Velocity is not an absolute property possessed by an object without qualification. A train may be moving rapidly relative to the ground while remaining at rest relative to a passenger seated inside it. Neither description is false. Each refers to a different physical frame of reference. Relational quantum mechanics suggests that quantum properties may possess a similar dependence on physical relations. A state can be definite relative to one system while remaining in superposition relative to another. The comparison should not be stretched too far. Albert Einstein's relativity and relational quantum mechanics are different theories with different mathematics and different meanings. The analogy simply helps show that dependence on a reference does not automatically make a quantity unreal. Relational quantum mechanics attempts to dissolve the measurement problem by rejecting the assumption that every observer must assign the same state at the same moment. In the traditional measurement problem, a detector appears to record one outcome while the Schrödinger equation preserves a superposition in the larger wave function. The two descriptions seem incompatible only if one absolute state must apply universally. The relational approach allows the detector to possess a definite result relative to the measured particle, while another system still assigns an entangled state to the combined arrangement. No physical collapse visible from every possible perspective is required. This avoids the need for a special boundary between quantum and classical objects. Every system can be treated quantum mechanically, and every measurement is an ordinary interaction. Yet difficult questions remain. Suppose two observers measure the same system separately, and later meet to compare their records. Their accounts must display a consistent pattern when they interact. One observer should not find that the other has recorded an impossible result or remembers a history incompatible with the physical correlations between them. Supporters argue that quantum mechanics guarantees this consistency through the structure of later interactions. When observers compare records, they establish new relations, and the resulting correlations obey the ordinary quantum rules. Critics continue to debate whether this fully explains how shared, stable reality emerges. If facts are always relative, It must still be shown why the macroscopic world appears so reliably common to many observers. Environmental decoherence may help. Information about events becomes copied into photons, air molecules, instruments, and surrounding objects. Many systems then acquire matching correlations, creating the appearance of a broadly shared classical record. Even so, questions remain about whether relational facts alone are sufficient to describe the entire physical world, and whether a universal wave function can be completely abandoned. The interpretation gives the wave function a position between two familiar extremes. It is not necessarily a universal physical substance spread across configuration space, nor is it merely private ignorance belonging to a human observer. Instead, it may describe the physical relationship between systems. It tells one system what probabilities and properties apply relative to another. In this view, asking whether the wave function is absolutely real may already assume too much. The deeper reality may not consist of isolated objects carrying complete states of their own. It may consist of the relations formed whenever one part of the universe encounters another. The wave function cannot be placed beneath a microscope and photographed as though it were a tiny object. Its reality must be investigated indirectly, by asking which possible accounts of the world can reproduce the predictions of quantum mechanics. This is the purpose of quantum ontology theorems. They begin with broad mathematical models of what might exist beneath the quantum state, then determine whether those models are compatible with experimental predictions. In such a model, a system is assumed to possess an underlying physical state. This is meant to represent a complete specification of reality at a given moment. The underlying state need not be a classical particle carrying a secret position or velocity. It could be almost any deeper collection of properties, including structures that have no familiar mechanical interpretation. The important assumption is simply that something describes the system's actual physical condition. Different laboratory preparations may then produce different probability distributions over these underlying states. This framework allows physicists to distinguish between wave function ontic and wave function epistemic models. In a wave function ontic model, distinct wave functions correspond to distinct underlying physical realities. If the complete underlying state were somehow known, it would reveal which wave function had been prepared. In a wave function epistemic model, two different wave functions may correspond to overlapping ranges of underlying states. The same physical reality could therefore be compatible with more than one quantum state, much as one actual card may be included within several different descriptions of an incompletely known deck. The wave function would then resemble knowledge about reality rather than reality itself. A powerful restriction on this possibility was developed by Matthew Pusey, Jonathan Barrett, and Terry Rudolph. Their theorem was published in 2012 and is commonly known by the initials of their surnames, although its conclusion requires careful wording. The theorem considers systems prepared independently. Preparation independence means that when two systems are produced separately, with no shared preparation process, their underlying physical states are assumed to be independently distributed. Imagine two laboratories preparing two particles without coordinating their hidden details. The complete physical state of one particle should not secretly determine the complete physical state of the other, merely because both will later appear in the same argument. Now suppose two distinct wave functions can sometimes correspond to the same underlying state. Their probability distributions overlap. A preparation device may produce one wave function or the other, while the deeper physical reality occasionally turns out identical. If several systems are prepared independently, these overlaps combine. There is then a non-zero possibility that different combinations of quantum preparations produce the same overall underlying physical state. A carefully chosen joint measurement creates the difficulty. Quantum mechanics predicts that each possible measurement result is impossible for at least one of the preparation combinations. Yet if all those combinations can share the same underlying physical state, the deeper model cannot always know which outcome must be forbidden. The overlapping epistemic model is then forced into a prediction that conflicts with quantum mechanics. Under preparation, independence, and the theorem's other assumptions, distinct pure quantum states must therefore correspond to non-overlapping underlying realities. The complete physical state must contain enough information to determine the wave function. This is a strong result. It rules out a broad class of models in which the wave function represents only ordinary incomplete knowledge about a deeper state. It does not prove that the wave function is a material wave. It does not show that configuration space is a literal physical arena, establish the many worlds interpretation, or confirm pilot wave theory. The theorem works within a particular ontological framework. Interpretations that reject preparation independence, deny that independently prepared systems possess independent underlying states, or treat quantum states as relational or agent-dependent may not fit its assumptions. Other physicists have developed related results. Lucian Hardy showed that wave function epistemic models face strong restrictions under a different assumption called ontic indifference. Roger Kolbeck and Renata Renner argued that, given a suitable freedom of choice assumption, the wave function is uniquely determined by a complete underlying physical state. These arguments approach the question from different directions and rely on different premises. Their conclusions should not be merged into one universal proof. Debate continues over the meaning, necessity, and physical justification of the assumptions involved. Quantum ontology theorems have nevertheless changed the discussion. They show that treating the wave function as ordinary ignorance is not as easy as comparing it with an unknown card or an unseen molecule. Any deeper theory must reproduce interference, entanglement, and the precise statistical structure of quantum mechanics. Once reasonable-looking assumptions are added, many simple epistemic models become impossible. The wave function has been cornered more tightly than before, but it has not been forced to confess exactly what it is. Experiments are extraordinarily good at telling physicists what quantum mechanics predicts correctly. They are much less direct when asked what the wave function itself truly is. The difficulty begins with a simple fact. Most established interpretations of quantum mechanics were designed to reproduce the same ordinary laboratory results. Copenhagen approaches, pilot wave theory, many worlds interpretations, relational quantum mechanics, and several informational views all agree on the probability expected in standard experiments. They disagree about what exists behind those probabilities. If two interpretations predict the same detector clicks, interference patterns, and atomic energy levels, then repeating those experiments cannot easily distinguish between them. The apparatus records an outcome, but it does not attach a philosophical label explaining whether the wave function collapsed, branched, guided a particle, or represented an observer's expectations. One of the most important experimental tools for studying quantum states is quantum state tomography. The name suggests taking an image of a quantum system, but the process is less direct than an ordinary scan. Quantum state tomography reconstructs a wave function, or a density matrix, from the statistical results of many measurements performed on many systems prepared in the same way. A single electron cannot usually be measured repeatedly in every possible basis while remaining untouched. Measuring one property changes what can later be learned about another. Instead, researchers prepare a large collection of systems as identically as possible. One group may be measured for position, another may be measured for momentum, others may be tested in different spin directions or through different interference arrangements. The accumulated statistics are then combined to reconstruct the quantum state that best explains the results. This procedure can be extremely precise. It allows physicists to characterize the states produced inside quantum computers, optical experiments, trapped ion systems, and many other technologies. Yet reconstruction does not automatically establish physical reality. A weather service can reconstruct a probability distribution for tomorrow's temperature without implying that the distribution is a material cloud floating above the city. In the same way, reconstructing a wave function shows that one mathematical state successfully organizes the observed statistics. It does not by itself prove that the wave function is a physical substance. Another approach involves weak measurement. The theoretical foundations of weak measurement were developed by Akir Aharonov, David Albert, and Lev Weidman. Instead of strongly coupling a measuring device to a quantum system and forcing a clear result in one trial, a weak measurement uses an extremely gentle interaction. Each individual reading contains very little information and is dominated by uncertainty. The system is disturbed only slightly, but the result from one trial is almost useless on its own. When the experiment is repeated many times, however, the tiny statistical shifts can be averaged. Researchers can then extract information about the prepared quantum state, while reducing the disturbance applied to each individual system. Weak measurements are often combined with post-selection. After the gentle interaction, only systems producing a chosen later result are included in the final analysis. Some experiments using this method have been described as direct measurements of the wave function. In certain arrangements, the average weak measurement results can be related closely to the complex amplitudes of the state. The phrase direct measurement should still be treated carefully. The procedure relies on many repeated preparations, statistical averaging, post-selection, and a theoretical framework connecting the measured shifts to the wave function. It does not involve watching one untouched wave function quietly waving in front of a camera. The result is direct in a specialized operational sense. It provides a route from measured statistics to wave function amplitudes without requiring every step of traditional tomography. It does not settle whether those amplitudes represent a material entity, information, or relations between systems. Experiments have also been inspired by quantum state ontology theorems. These investigations ask whether different quantum states can correspond to overlapping distributions over deeper physical states. Rather than testing the vague statement that the wave function is real, they translate the question into specific mathematical models. A laboratory can prepare several quantum states and perform carefully chosen measurements designed to reveal whether those preparations could share the same underlying physical description. Results can then exclude particular classes of models, provided the assumptions behind the analysis are accepted. Some experiments have placed strong limits on simple wave function epistemic models, in which different quantum states overlap like ordinary probability distributions over hidden classical realities. The limitation is essential. An experiment does not test the abstract word real by itself. Reality must be given a mathematical definition that produces observable consequences. Researchers must specify what deeper states are allowed, how preparations relate to them, and which independent assumptions the model satisfies. When a result rules out such a model, it rules out that defined possibility. It does not automatically prove every realist interpretation or eliminate all informational and relational alternatives. Objective collapse theories offer a clear opportunity for direct testing because they alter the dynamics. Instead of interpreting the ordinary equations differently, they add a genuine collapse process. Depending on the model, this may produce spontaneous localization, faint radiation, tiny energy increases, unexplained heating, or a loss of interference beyond a particular mass or scale. These effects can be searched for experimentally. Matter wave interferometers test whether increasingly large systems remain coherent. Optomechanical experiments examine tiny vibrating mirrors, membranes, and resonators. Precision detectors search for unexplained noise or radiation. If a collapse theory predicts an effect that fails to appear, its allowed parameter range becomes smaller. No confirmed signal has yet shown that objective collapse occurs. At the same time, matter wave experiments have demonstrated interference in systems far larger than single electrons. Atoms, clusters, and complex molecules can be placed into coherent superpositions and sent through interferometers. In carefully controlled conditions, objects containing many atoms produce patterns governed by their matter wave amplitudes. These experiments show that quantum coherence is not restricted to the smallest known particles. The boundary between quantum and classical behavior is not set simply by calling something a molecule rather than an electron. Even so, maintaining interference becomes harder as systems grow. Larger objects interact more strongly with stray gas particles, thermal radiation, vibrations, and other environmental disturbances. Decoherence can hide the interference long before any hypothetical fundamental collapse becomes important. Observing interference in a large molecule therefore confirms the continued success of quantum mechanics at that scale. It does not reveal whether the underlying wave function is a real object, a guiding structure, a branch-containing state, or a compact representation of information. Experiments steadily narrow the range of acceptable stories. They rule out local hidden variable models, constrain simple epistemic theories, test collapse mechanisms, and confirm quantum coherence across increasingly complex systems. What they have not produced is one universally accepted image of the wave function's ontology. The wave function can be reconstructed, manipulated, and tested through the probabilities it predicts. Its coherence can be preserved or destroyed. Its mathematical consequences can be observed with extraordinary accuracy, but no experiment has yet made every physicist agree on what the wave function is. The laboratory can corner particular theories. It cannot photograph the meaning of reality itself. Physicists still do not know whether the quantum wave function is real. That statement does not mean they are unsure how to use it. The opposite is true. The wave function sits at the center of one of the most successful theories ever created. Physicists can calculate how it evolves, use it to predict experimental outcomes, reconstruct it from repeated measurements, and test those predictions with extraordinary precision. What remains unsettled is what the wave function represents. The puzzle began when the old classical categories stopped working. In classical physics, particles occupied definite positions and followed continuous trajectories. Waves were extended disturbances spread through space, carrying amplitude, phase, and wavelength. Matter behaved like matter, while waves behaved like waves, and the distinction appeared comfortably clear. Then Max Planck showed that energy exchange could occur in discrete quantities. Albert Einstein argued that light transfers energy in localized packets later called photons, even though light had already demonstrated unmistakable wave behavior. Louis de Broglie extended the reversal by proposing that particles of matter possess wavelengths related to their momentum. Electrons then diffracted from crystals. Individual particles arrived as localized detections, while many detections accumulated into wave-like interference patterns. Erwin Schrödinger responded by developing wave mechanics. His equation described how a quantum state changes through space and time, and successfully reproduced the discrete energy levels of atoms. Electrons were no longer represented as tiny planets circling nuclei along narrow paths. They occupied wave function states with particular energies and spatial structures. Max Born then supplied the crucial statistical interpretation. The wave function itself was not read directly as a probability. Instead, the probability of obtaining a result is determined by the squared magnitude of the corresponding wave function amplitude. This made the theory operationally complete. The Schrödinger equation described how the state evolves. The Born rule connected that state to experimental frequencies. Yet the wave function contains more than a list of chances. Its amplitudes possess relative phases. Those phases determine how different possibilities combine. In the double-slit experiment, amplitudes associated with two paths can reinforce one another in some regions and cancel in others. The result is an interference pattern that cannot be reproduced by treating the particle as merely following one unknown classical route. A hidden card has one definite identity, even when nobody knows it. Its possible identities do not interfere. Quantum alternatives do. This makes the wave function difficult to dismiss as ordinary ignorance. Whatever it represents, its internal structure has observable consequences. The difficulty becomes greater when more than one particle is involved. A single particle's position, wave function, can be represented across ordinary three-dimensional space, which makes it tempting to imagine a familiar physical wave. But the complete wave function of two particles generally depends on 6 spatial coordinates. 10 particles require 30. For a large entangled system, the wave function naturally belongs to a configuration space with an enormous number of dimensions. If the wave function is physically real, its most natural mathematical home appears very unlike the space through which tables, atoms, and observers seem to move. Perhaps configuration space is fundamental, and the ordinary world emerges from patterns within it. Perhaps configuration space is only an abstract arena used to organize possible arrangements. The mathematics does not settle the issue by itself. Measurement creates another divide. Between measurements, the wave function evolves smoothly and deterministically according to the Schrödinger equation. A superposition remains a superposition. Yet an experiment produces one definite result. Textbook quantum mechanics introduces collapse, replacing the superposition with the state corresponding to the observed outcome. The difficulty is that this collapse is probabilistic and apparently discontinuous, while ordinary evolution is continuous and deterministic. Why should one rule apply before measurement and another during it? What precisely counts as a measurement? At what point does the transition occur? Environmental decoherence explains much of what makes the world look classical. Interactions with photons, air molecules, thermal radiation, and surrounding matter entangle a system with its environment. Phase information becomes dispersed into vast correlations, making interference between macroscopically different alternatives practically inaccessible. Decoherence explains why measuring pointers produce stable records, and why chairs do not visibly interfere with themselves across the room. It explains why certain classical-looking states remain robust, while delicate superpositions become hidden. What it does not establish unanimously is why one unique outcome is experienced if the complete wave function still contains several decohered alternatives. Different interpretations answer by changing what the wave function is allowed to mean. Copenhagen approaches avoid assigning one unrestricted mechanical reality to quantum systems between observations. They emphasize experimental arrangements, definite records, and the limits of classical description. The wave function may be indispensable without being treated as a material object. De Broglie-Bohm theory gives particles definite positions and treats the wave function as a real guiding structure. The particle follows one trajectory while the guiding wave carries the interference structure associated with several possible routes. Everettian quantum mechanics removes collapse altogether. The universal wave function always evolves according to the Schrödinger equation, and decohered outcomes become effectively separate branches. In this view, the wave function is not merely part of reality. It is the fundamental structure from which classical worlds emerge. Objective collapse theories take the opposite route. They modify quantum dynamics so that collapse becomes a genuine physical process. The wave function is real, and sufficiently large superpositions are spontaneously reduced to definite states. Quantum Bayesianism treats the wave function as an agent's probability assignment concerning the consequences of interacting with the world. Collapse is then an update in expectation rather than a physical wave contracting through space. Relational quantum mechanics makes the state meaningful relative to interactions between physical systems. A quantum property may be definite relative to one system, while remaining in superposition relative to another. Each account preserves the predictive success of quantum mechanics, while presenting a different ontology. The theorem developed by Matthew Pusey, Jonathan Barrett, and Terry Rudolph narrowed the range of possibilities. Under assumptions including preparation independence, it strongly restricts models in which different wave functions merely overlap as incomplete knowledge of the same underlying physical state. The theorem shows that the wave function cannot always be treated like an ordinary probability distribution over hidden classical facts. But it does not prove that the wave function is a material field. It does not establish configuration space realism, many worlds, pilot wave theory, or objective collapse. Interpretations that reject or modify its assumptions remain open. The word real therefore conceals several separate questions. Is the wave function fundamental, or does it emerge from something deeper? Is it matter, information, relation, or law? Does it physically inhabit configuration space? Does collapse occur? Does a quantum state belong absolutely to a system, or only relative to another system or observer? Physicists agree on the calculations because experiments force agreement. They disagree on the ontology because the same successful formalism can support several incompatible accounts of what exists. The wave function may be a physical structure. It may organize information. It may describe relations. It may guide particles, contain branches, undergo genuine collapse, or eventually be replaced by a deeper theory. Whatever its final meaning, it remains indispensable. It predicts atoms, molecules, interference tunneling, chemistry, lasers, electronics, and the quiet behavior of matter beneath everything familiar. It has survived roughly a century of increasingly precise tests while refusing to reveal one universally accepted identity. That may be what makes the wave function the most successful mystery in physics. We still do not know exactly what it is, but almost everything quantum mechanics can tell us begins with it.